You probably file sulfuric acid under school chemistry. A bottle with a warning label, maybe the stuff inside a car battery. Wrong scale entirely. It is the most produced industrial chemical on Earth by mass, somewhere on the order of 250 to 300 million tons a year, and almost none of it ever ends up in a product you can buy. It is the chemical industry's workhorse. If something was manufactured, refined, or mined, this acid was in the process somewhere. So where does 250 million tons a year actually go? Its single biggest job is food. Roughly half of world production is used to dissolve phosphate rock into phosphoric acid, which becomes fertilizer. That puts the acid supply directly upstream of global agriculture, not adjacent to it, upstream of it. Here is where it gets strange. You would assume something this important gets mined on purpose. It mostly doesn't. Overwhelmingly, the sulfur behind the world's acid is a byproduct of cleaning fossil fuels, stripped out of sour natural gas and out of oil at refineries because regulations demand sulfur come out of fuels. Those stinking yellow mountains you see stacked beside refineries are the world's acid supply, waiting. That one fact rewires the whole market. Nobody is producing sulfur because acid buyers want more of it. The supply is set by how much fuel got refined and desulfurized. So when demand spikes, producers cannot simply make more. That is why the spot price is violent. Historically, it has swung by an order of magnitude inside a couple of years. Meanwhile, the fastest growing customer is the energy transition. Acid leaching is how you pull metals out of stubborn ore. Nickel laterites for batteries, copper oxide heaps, cobalt, rare earth processing. This is consumption by the megaton. One large nickel high-pressure acid leach plant can eat more than 1 million tons of sulfuric acid in a year by itself. Now put those two things side by side and see the trap. Decarbonization shrinks oil and gas processing. Shrinking oil and gas processing shrinks byproduct sulfur. And it happens exactly when battery metals are pushing acid demand up. A 2022 University College London study flagged a potential shortfall of tens to hundreds of millions of tons of sulfuric acid by 2040 under fast decarbonization scenarios. Could we just make sulfur deliberately instead? Yes, and every option is worse. You can mine elemental sulfur or roast pyrite, iron sulfide, the way China still does at scale. Both are dirtier and more expensive than scooping up a leftover at a refinery, which leads somewhere genuinely absurd. A green energy world may end up reopening sulfur mines to feed its battery plants. Then there is the small matter of moving the stuff. Concentrated sulfuric acid is heavy and corrosive, and it travels in dedicated tank cars, dedicated ships, and pipelines. Hauling it a long way costs real money. So shortages are regional rather than global, and fertilizer plants and smelters cluster around wherever the supply already is. Smelters are the other tap. Copper, zinc, and nickel smelters capture their sulfur dioxide off gas and turn it into acid, what the trade calls smelter acid, which means an environmental crackdown or a single smelter closure in one country can ripple through acid markets on another continent. The chain is that tight and that invisible. And almost nobody outside the industry watches any of this. There is no meaningful sulfuric acid futures market. There are no headlines. Yet fertilizer, batteries, copper wire, paper, detergents, and pharmaceuticals all sit downstream of it. A commodity with no fan base and no ticker, quietly holding up the things everyone else argues about. Here is my take. Everyone maps the lithium mines and the chip fabs because those photograph well. But the economy also runs on boring intermediate chemicals nobody cheers for, and sulfuric acid is the biggest of them all. It is the bloodstream of heavy industry, and we source it as a leftover from the exact fossil fuel system we are trying to shut down. Killing oil without a sulfur plan is the kind of second-order problem that makes energy transitions much harder than the slide decks admit.